All right, this is part 2 of 11.1, the review of sequences. When we're doing sequences, we've already kind of done a lot of the nuts and the bolts. We're going to deal with convergence and divergence of a sequence, because you can actually talk about convergence or divergence of either sequence or series. We'll talk about series next section. Convergence of a sequence means that as you go off to infinity, as you approach infinity, the outputs of your function are going to approach a finite recognizable number. So what this really is just end behavior. Okay, so if we're given something like a sub n is equal to the cube root of n over the cube root of n plus 1, I mean, in our head, we should remember that, if we have something like this, did this have a horizontal asymptote as x goes off to infinity? Because if this has a horizontal asymptote, then this is convergent, okay? So it's the same sort of idea, and that's why I emphasized in the last video that these are functions, okay? So the difference between this and this is the fact that this has inputs that are natural numbers, and this has inputs that are all numbers, except, -1. So this has a domain that exists on an interval. This has a domain that exists as simply the natural numbers. But the question is the same, right? The question for end behavior asymptote, which in this case gives you a horizontal asymptote. If this has a horizontal asymptote, then that should have implications for what this means over here, okay? Because the only difference between this is the type of numbers that can be included here. This, by nature of it being a sequence, has a domain of natural numbers. So all integers going in the positive direction starting with 1, okay? Now, they're both going to infinity. Now remember the rules for end behavior asymptotes. If here we have the same degree in the numerator as the denominator, then the limit is simply the ratio of the leading coefficients. This should be 1. This should be 1 as well. This tells me that this sequence is convergent. It converges at a value of 1. And if you just think about it numerically, that should actually make sense to us. You plug in 1, you get 1/2. You plug in 2, well, it's a little bit more than 1/2. You plug in 8, right, and you're going to get 2 over 3, so it's 2/3. You plug in 27, and you're going to get 3/4. You plug in 64, you're going to get 4/5, right? But as you increase and increase and increase the numbers that you're plugging in for n, this +1 numerically starts to matter a whole lot less in terms of being a sort of player in determining the value of that ratio. If you're plugging in, 2 billion, that +1 is kind of negligible. At 2 billion, that ratio is functionally 1. Now, it isn't officially 1. It's just sort of functionally 1 because, the +1 really has failed to really make a significant difference on the value of that ratio, okay? So what we need to do is we simply need to take the limit as x approaches infinity and try to determine whether it actually has a recognizable numerical limit, okay? Okay, well, what's going on there? Well, let's actually list out a couple of these values. If I plug in 1, okay, I'm going to get 0 over 1 squared. If I plug in 2, I'm going to get 2 over 2 squared. If I plug in 3, I'm going to get 0 over 3 squared. If I plug in 4, I'm going to get 2 over 4 squared. If I plug in 5, I'm going to get 0 over 5 squared. Now, whether it's an even or an odd number, just flips this to -1, +1, -1, +1, -1, +1. When it's -1, it cancels out with this. When it's +1, it combines with this, hence the 0, 2, 0, 2, 0, 2 all the way out, okay? And of course, the denominator is getting really, really large as it goes off and becomes, 6 squared, 7 squared, a billion squared, whatever. So just looking at this string of numbers, we know that it doesn't proceed, easily or sort of in a consistent manner towards a specific number, but we do recognize the fact that every other term is 0, and every other term, every even term is getting smaller and smaller and getting towards 0, okay? And what you need to know here, basically as n gets really, really large, whatever that numerator is becomes really, really insignificant, okay? So as we take the limit as n approaches infinity of 1 plus -1 to the n of n squared, this just winds up oscillating back and forth between 0 and 2, 0, 2, 0, 2, 0, 2, 0, 2. This gets insanely large. That's going to 0. That converges at 0. Okay? Now, let's do another one. Let's say we have a sub n is equal to the natural log of square root of n over n. Now, we've talked about the general sort of power of different classes of functions, and I know that a linear is more powerful than a natural log function. I know that it increases faster than a natural log function, but just for the sake of actually showing it analytically, what we need to do is, of course, it's probably a good idea to bring that out, or you can even put natural log n over 2n. Now, what is the limit as n approaches infinity of natural log n over 2n? Now, I can sort of talk my way through this and reason my way through this, but remember that if I actually plug in infinity, this is infinity over infinity. That's indeterminate, which means that I can actually use L'Hopital's rule by taking the derivative of the numerator and the derivative of the denominator, which becomes the limit as n approaches infinity of 1 over 2n, and that most assuredly is 0, and therefore it is convergent, right? It converges towards a finite recognizable number. Okay, well, let's get to a couple more that are a little bit more robust and cause us to think just a little bit and review some concepts that perhaps we haven't seen in a little while. Let's say that we have that. And remember, that's not being really excited about n plus 1 and not being really excited about n. It's not n, it's n factorial, right? And so we have, 4 factorial is 4 times 3 times 2 times 1, and 5 factorial and all that sort of fun stuff. So let's say all we know is that what's being done in the numerator is 1 greater factorial, right? So if the numerator is 4 factorial, the denominator is 3 factorial, right? And that's 3 times 2 times 1. Do you see how that happens right there? And so what we can do is sort of finagle it just in general. I know that n plus 1 factorial is actually n plus 1 times n factorial, just like 4 factorial is 4 times 3 factorial, right? And so, and we've done this before, 12 factorial is 12 times 11 factorial, or 12 times 11 times 10 factorial, or 12 times 11 times 10 times 9 factorial, right? And so all we've done is we've taken what we've been able to do in terms of numerical factorials and sort of changing the form for the sake of simplification, and we've simply done it here. Now those obviously cancel out, and a sub n is just n plus 1. Well, I got news for you. When you take the limit as n approaches infinity of n plus 1, it's infinite, okay? And therefore this is a divergent sequence. Now there are other examples of this. But we do actually need to get, let's do one more and then we'll get to the final discussion that we have of sequences before we move on to series. Let's do a sub n is equal to n squared over 2n plus 1 minus n squared 2n minus 1. Now, if I were to actually take the limit, that would be infinity minus infinity, and it really wouldn't get us anywhere. So what we probably need to do is we probably need to get a common denominator. Okay. Now that winds up being 2n cubed minus n squared minus 2n cubed, or that's, yeah, it's minus n squared over 4n squared minus 1. Well, that crosses out with that. I'm going to get a negative 2n squared over 4n squared minus 1. Now the limit of that is very easy. We have the limit as n approaches infinity of negative 2n squared over 4n squared minus 1. Now we can either do this by the algebra 2 method, where we just look at the leading coefficients since they are the same degree. We could actually do it by a more rigorous infinite limits by, multiplying it by 1 over n squared and 1 over n squared. Let's do at least one example that way. And we're going to get negative 2 over 4 minus 1 over n squared. As n goes to infinity, that bad boy goes to 0, and I'm left with just negative 2 over 4, or negative 1/2. That is a convergent sequence because it actually goes towards a recognizable finite number. I hope that's enough examples for that. The last little bit of this video, I want to discuss something that it's kind of useful, I suppose. I was never a big fan of this sort of lingo. You know me. When the vocabulary is necessary, I want you to learn it. When the vocabulary is not necessary, and I think it's basically just a whole big waste of time, I mention it in passing and we move on. I'm unsure about whether your teacher is going to find this compelling and whether she's going to want to bring it up. But since these are functions, let's say I have a sub n and I have 3n over n plus 2. Can I figure out whether that is increasing or decreasing? Of course I can. Okay, so what happens here is, let's go ahead and remind ourselves what we would do if we were asked whether that was increasing or decreasing. Well, we would take the derivative, right? If we take the derivative of this, we get the bottom times the derivative of the top minus the top times the derivative of the bottom, all of that over the bottom squared. And that winds up being 3x plus 6 minus 3x, all of that over x plus 2 squared, or 6 over x plus 2 squared. Now that's the derivative. So if I were to actually take the derivative of this function, it would be the same, except it would just be n's, right? But I happen to also know that the domain of this, right, is only positive integers. So when positive integers are plugged into something like this, well, the numerator is positive, it's 6. The denominator is squared, so it's always non-negative. The only time this is 0 is when it's negative 2. So I know on this domain, the derivative is always positive. This is always increasing. Okay? So when a function is always increasing or always decreasing, meaning that it never changes direction, it never goes from positive to negative slope or negative to positive, it never goes from increasing to decreasing, never goes from decreasing to increasing, when it's always increasing or decreasing, the name for that is monotonic. Okay? I don't really care about that. It's language that my calculus teacher spoke when I was in high school, but I sort of made a judgment call when I was teaching my own calculus class that that sort of language really wasn't all that important. But if you ever hear somebody speak of a monotonic function, it is a function that is always increasing or always decreasing. Okay. Now, if you hear about something that is, if you hear about a bounded sequence, that is exactly what it sounds like, okay? That basically means that, okay, there is a number m, okay, that a sub n never goes above, okay, and there is a number, and we'll call this one maybe small m, so big M for maximum, small m for minimum, that a sub n never goes below. Okay, so graphically speaking, a bounded function would be one, that basically exists, within a range like this between big M, which is your max, and your min. Basically, it happens in here. And of course, something that we'd be very familiar with is like sine function. A sinusoidal curve would be a bounded function. And therefore, we've already seen one like that. We've already seen the fact that a sub n is equal to sine of pi n over 2. That was a bounded function. All that gave us was 1, 0, negative 1, 0, 1, 0, negative 1, 0, and it keeps doing that on and on and on. It's never going to go above 1. 1 would be my big M. It's never going to go below negative 1. That would be my small m. This is a bounded sequence, right? It basically exists between upper boundaries and lower boundaries. And so, they name it on purpose, and so the name should actually, describe what's going on. There is a theorem in your book that states, and it's called the monotonic sequence theorem. And I don't really care that you memorize it because I just want to explain the logic. The logic behind it is very, very simple. The monotonic sequence theorem basically says if a sub n is monotonic and bounded, then it must be convergent. Well, that just kind of makes sense, doesn't it? Okay. So basically what you're saying is if you have a function that has an upper boundary, it's always increasing, but it never goes past that boundary, then of course it's going to hug that boundary, right? If it's always increasing but never goes above a particular boundary, then that's basically definitionally what we refer to as a horizontal asymptote, or at least one of the ways in which a function can come up and approach a horizontal asymptote and hug it as it goes off to infinity. And the same thing if it's monotonic being always decreasing towards, a minimum, right? And basically if you have a minimum and an always decreasing function and it's bounded, then it's going to go towards this number. And of course, we already made the connection between horizontal asymptotes of our functions that we were used to dealing with. Our, f of x is equal to some sort of rational function or rational-ish function. So basically the whole idea of this is if it's always increasing but never goes above a certain boundary, then it actually hugs that boundary and is convergent. If it's always decreasing but never goes below a certain boundary, then it's going to hug some numbers that goes off to infinity and is therefore convergent. Now, so if your teacher doesn't require you to memorize this, I still think it's instructive to actually know the logic behind it, okay? That brings our discussion of 11.1 to a close. We'll go ahead and start on 11.2 and do a little work in 11.2 before we start moving into new material, which would of course be the convergence and divergence tests of 11.3 through 11.7. As always, if you have any questions, please do email me. Bye.